So radiation that comes from space, whether it's radio, optical, infrared, ultraviolet, actually comes in two different forms. We refer to these things as polarization. The radio waves that can be thought of as propagating in two orthogonal, that is to say, right-angle planes. These two waves, which any electromagnetic wave can be decomposed into, are completely independent, and they provide us, the astronomer, with extra information about the magnetic fields, information about the molecular transitions, and it's important that when we design our instruments, we're able to measure these two components of the radio wave separately and independently and correctly. To do this, we have very specialized devices, often referred to as Orthomode Transducers, which are responsible for separating the radio wave into its component parts. We have with us here a number of examples of these devices for these lower frequency bands where these devices are large enough that we can pick them up and show. So Bob, explain how these things work, where these things come from, and why they look the way they do.
Okay, so what we will start off talking about is the Orthomode transducer for our lowest frequency cooled receiver, and this is our 1 to 2 gigahertz L-band, as we call it. This thing looks pretty heavy, but it's maybe 20 to 30 pounds. It's all out of aluminum. It's been engineered by our mechanical designers to be as light as possible, hence all of these waffle looking things here to minimize the weight.
That's waffle, not awful. Bad joke. Go on.
So what our OMT has to do in this particular frequency is to transform the impedance of free space down to 50 ohms. All of our low frequency stuff works at 50 ohms impedance. And so we have to transfer 400 ohms, the impedance of a signal traveling in free space, down to the impedance of 50 ohms, which our coaxial components work at.
What's the relationship between this and the horn?
So at L-band, that big huge horn that you've seen on the antenna presents sort of a 400 ohm impedance. We got to convert that to 50 ohms. But more importantly, we have to do it over a very wide bandwidth. And so in engineering terms, it's called an octave bandwidth. In other words, the highest frequency is twice the frequency of the lowest frequency, so 1 to 2 gigahertz. So these quad ridge systems, and this is what we call it, is quad ridge OMT. You can see the four ridges, that's your quads. And what we have to do is use that to convert 400 ohms down to 50 ohms.
Okay.
And this particular unit here took about 5 years to develop. But the nice thing is that once you design it for one of our lower frequencies, it will work equally well, we hope, at all frequencies. And so we now have a version here that works at 2 to 4, and a version here that works for 4 to 8 gigahertz.
And these are all scale replicas of each other, right?
Yeah. And if we were to open up the S-band unit, you can see we've taken off one corner of the enclosures and removed one of the fins. So you see 1 fin, 2 fin, 3 fin, and then the 4th fin that would sit here. And so what you see is kind of a tapered feature here, which is what's used to do the translation of the 400 ohm impedance down to the 50 ohm impedance.
So we can think of the electromagnetic wave coming in on two orthogonal planes, right?
That's right.
And so the wave that's in this plane is working its way down through this ever narrowing to be picked off by something down here. Is that the way to look at it?
Yeah. And so if you here are our coaxial outputs from these receivers. So remember, we're waveguide at the front of it and coaxial at the end of it. And so we have 2 probes to pick up the 2 polarizations. So if we turn it around, you can see sort of one probe is down below, and then the second probe is here. So this is the probe that picks up the energy coming from the feed.
So this is the actual device that converts the electric field, whose units are, say, volts per meter,
Right.
into volts in that little wire.
That's correct.
Yeah. So I see before us here the largest for the longest wavelength, 1 to 2 gigahertz. The next largest, I think it's the same thing here, right, for 2 to 4 gigahertz. Then there's this littler one, 4 to 8 gigahertz. Everything scales with the wavelength. But what's this down here? It sort of looks the same, but it's also different. What have we got?
It's also different. It's was designed by Gordon Coots, and what it does is it works from 8 to 12 gigahertz, and he calls it an offset quadridge.
So these are all unique to this observatory and done by our own people. Is this right?
That's correct.